everyone, it's Sam, workshop coordinator here. Hope you are having a wonderful Wednesday today. Thank you so much for joining us for the ROC Game Dev's July workshop. We are very, very excited about today's speaker. Today, Aidan Markham will be presenting custom shaders in Unity, how to get started. Aidan is the lead technical artist and co-founder of Aesthetician Labs, an artist-owned video game cooperative best known for their Rochester-inspired arcade mobile game, Crazy Platez. Aidan is a teammate of mine, and I am so excited to have him present to you what he knows about getting started with shaders. So without any more dilly-dallying, I'm going to toss it over to Aidan.
Hello. So here we are, custom shaders in Unity. How to get started. Right up front, I've included this link. This will take you, now that's covered it, bit.ly/shader workshop, nice and convenient. That'll be good if you ever want to come back after presentation to remind yourself what was in the slides, or perhaps you just want to access the useful links page at the end. Another note, that useful links page at the end has a link to the GitHub repository that has all the files for the project that I'll be working in today. So if you ever wanted to get your hands in on the code, modify the scripts that I'll show you how to make today, you can just head right over to bit.ly/shader workshop. There's also a link to that available on my website, aidanmarkham.com. See that right here. So first, let's get into who I am. You got a picture of me here. As Sam mentioned, I'm the lead technical artist, co-founder, co-designer at Aesthetician Labs. We made Crazy Platez, and since then we've made really just a lot of other games. You can find me on Instagram at MarkhamAidan. It's probably my most active social. I'm also on Twitter at Aidan Markham, but I don't really post there too much. So let's get into it. What are we gonna learn? So there's a few takeaways here. We're gonna do a little bit of coverage on just how computers render 3D graphics, and sort of the role that shaders play in that process, and also some basics about how shaders work. The most important lesson, I think, of this workshop is how to avoid reinventing the wheel and just get to the fun part of shaders, where you get to make crazy, wacky effects happen on screen. And then to cap it off, we'll learn some of the building blocks of fun effects that you can make with shaders. Moving on. So how do computers show you pictures in terms of a 3D type environment? One note, I'm going to be talking about specifically Unity, which uses the CG shader language. There's also GSLS shaders, which are similar enough that you can easily do some Control F replace to translate shader code between the two of them. But this is all in the context of Unity. So first, a quick crash course on 3D graphics terminology. I'm going to use these terms a lot, so I just want to make sure that everyone's caught up on exactly what these things mean. So here we have a mesh. It's got vertices, vertex at each corner. In between those, there's edges, and then when you get enough of those together, you'll have a face. The reason it's called a mesh is because if you have one with enough complexity, it does look sort of like maybe there's a mesh covering the model. And here's an image that I got from the internet, which is a very, very simple version of how the render pipeline works. Again, I don't want to be scary with a lot of technical stuff here. I'm just trying to define some terms so that when I'm explaining things later in the technical part of this workshop, it'll all be clear. So those vertices we talked about earlier, they go into a vertex shader, and then that vertex shader does math to figure out kind of the angles that you're looking at them in. And I'll describe this more clearly as we move along. It undergoes rasterization, which turns geometry data into pixel data. A fragment shader, also known as a pixel shader, takes that pixel data and turns it into the actual image, and then it's rendered onto your screen. This slide's got a more text-based version of it. This will be handy if you ever come back to this presentation. It's a quick, simple crash course in how all this works. To run through it, the computer's got meshes. It sends that information to the GPU. The GPU does math to figure out where those vertices will be on the screen, it turns those vertices into pixels, and then it actually puts those pixels onto the screen. So shaders, they come in at two parts of this pipeline. The first one is the vertex shader, as I described. It handles the math that turns basically a list of points into the shapes that you see on screen. An important consideration, for example, is that if you aren't necessarily just looking at your scene from 0 to 0, you've probably got a camera that you want to move around through the scene, and so the actual positions of those points have to be transformed. And then the pixel shader, for example, maybe you don't want everything to just be white. Maybe you want lighting, or calculated on a pixel by pixel basis, or perhaps you want something with a texture on it. All of that is handled by the pixel shader. So one more time, let's real quick run down the difference between a pixel shader and a vertex shader. The vertex shader determines where on screen vertices, edges, and faces of a mesh are, and it runs once per vertex per frame. So if, for example, you had a cube which has 8 vertices, it would run for that particular shape 8 times per frame, which is, I'm not going to do that math in my head right now. It's a lot of times, but not nearly as many as the pixel shader, which runs once per pixel per frame. So on a 1920 by 1080 monitor in a game running at 60 FPS, the code that you write in your pixel shader will happen 124,416,000 times. And as I outlined here, that's a lot. So this is it's really one of my favorite parts about writing shaders is your code gets to be run so many times, over and over again, even. But a nice warning: don't be scared. All of that stuff I just talked about, Unity basically does for us, so we really hardly have to worry about it. We aren't going to be writing any shaders from scratch today. I think writing shaders from scratch can be very educational, but it's not the best way to get started because it requires you to learn so much before you get anything on screen. And lucky for us, all the shaders that Unity uses, every different material setting and everything, is available online for us to download and modify. And that's what we're gonna do today. We're gonna start with some shaders that Unity has already provided, and we're gonna modify them so that they have cool effects and crazy stuff that happens. A quick word of caution. When I started, I was like, all right, what shader do I want to modify? I'm going to modify the standard shader. Seems like a good starting point. But it is a colossus. It's so big. It's spread across, I don't know, something like 30 different text files. And it involves like so much very cutting edge technology. It makes it much harder to modify. So instead, I think a much nicer base to work with is the normal diffuse shader. And I've got this nice meme here to illustrate the difference between the two. Normal diffuse is much simpler and easier to work with. So let's get hands-on. Exit out of this here. So the first thing I'm going to do is I'm going to go ahead and download the shaders. I see we've got a couple people in here already. If you want to get to this page, I've included a link to it under useful links. Useful links called where to download shaders for your version of Unity. I'm using Unity 2019.4.0. So I'm just going to click here on this drop down and then click built-in shaders. And let's show that folder. We can see here we've got all the different shaders here. You go into default resources, there's some internal things, but really all the meat and potatoes is in default resources extra. Here we've got all sorts of different fun things we can work with. But before we get into that, let me cover the template project I have set up. And this is all available on GitHub, so you can download this and check it out. So here I've got a nice little scene. We've got 2 survivors and 2 zombies, and then a simple background. All of these assets are from kenny.nl. It's the nature pack, and I think it's called, I've got it here in scene assets. It's the animated characters 1 pack. And if we click run, you can see, once it compiles, that the characters run along, and with the help of a simple parallax script, just shifts things forward. So we essentially have an endless little scene of the characters running here. And this will serve as a useful kind of test bed for us to build our shaders on top of. So the first shader I'm going to talk about writing is the very first shader that I ever wrote. I think it's useful in maybe not a huge amount of situations, but I found myself always wanting it when I want to do so. So I have a cube. I'm going to create a material for it. Call it cube. And now say I want this cube to be unlit. I have the option of a color material, which lets me change the color of the cube, or I have the option to use a texture, which, for example, I can put this checkerboard texture on it. But what if I wanted to color this checkerboard texture? The standard shader lets you color the checkerboard texture, but I don't want the standard shader. I want it to be unlit, so there's no lighting at all. Well, lucky for us, that's a pretty simple shader to work with, and a great way to learn some of the very basics of how shaders work. So the first thing I'm going to do is I'm going to grab from the built-in shaders the shader that I want to modify. So the unlit texture shader already has the texturing built in. I don't want to rewrite the texturing. I just want to add a color to it. So it's in default resources extra. If I scroll down, where is it? Somewhere in here. It's in the folder unlit. Yeah, unlit normal is what it's called. So I'll just drag that into the project. Now we have our unlit normal shader. And I'm going to go ahead and rename it right now. I'm going to call it unlit tinted texture. How about that? I like to use Visual Studio to write my shaders because it's what I'm used to. However, the vast majority of Visual Studio features don't actually work with shaders, but I like it does enough. It colors the text where I want it to color the text, and it has a lot of integrations that work well with Unity. Yes, that's a good, very good point. All right, so here we go. Is this better? Yeah, awesome. So the first thing I'm going to do is I'm going to give this shader a place for Unity to find it. So if you see, that's unlit texture. When I was here on the cube material, that's just this hierarchy here. So I'm going to call it workshop / tinted texture. If you come back into Unity, and I select my cube material, you can scroll down, you can show workshop, and then here's tinted texture. But right now it's exactly the same as the material before. So let's add the color. Now I could just type it in here, but what I'm actually going to do is let's take a look at unlit color and see how it works. Visual Studio loves to jump in front. So if we look at unlit color, it's got unlit color. There's a list of properties, so it just has a color. Similarly, in tinted texture, which is the unmodified, just textured version, it only has a texture. And if we scroll down to the fragment shader, also known as the pixel shader, we can see here that it gets a color from that color, and then it does some stuff to make it compatible with fog and with alpha. We don't need to worry about that too much. Yeah, that's all really IDEs are for, is they color the text where you want them to color the text. And then it returns the color. So what we're gonna do is I'm just gonna copy this. We'll use this line directly, and we'll just place it directly below the main texture. And if I save and go back into Unity, we'll see that now we have the color property here. Unity reads that as a property. But that's not quite all that needs to be done in order to access the color. Because shaders run on the graphics card, they're a little bit decoupled from kind of the rest of the code of your project. And the way that Shader Lab, which is Unity's kind of shader integration, works is you have your properties, and this is the way that Unity supplies data, but you also have to define it down here in the body of your subshader, which for the case of most of the shaders that you'll work on when you're starting to modify shaders, there'll only be one. Sometimes with more complicated shaders, you can do multiple passes so that you can do even more stuff per frame. But so if we scroll down here, we can see that main text is here. So I'm just going to drop this right below that. And I'm going to use the data type fixed4. Fixed4, it's similar to float4, except for it has less precision. For colors, we need far less precision than we need for vertex data. And then it needs to be exactly the same name as up here. So color, color. The reason that I also have 4 instead of 3 is that this is a color with alpha. So it has the red value, the green value, the blue value, and then the alpha value. But we won't be using the alpha value for this shader here. So now, down in the fragment shader, I can access this color. So just to get started, let's first just define this call as color, replacing this. And I'll explain exactly what this means in a second. So if we come in here, now we can see our color is reflected on the cube. And so let's take a look at what's actually happening here. So this method text2d is short for texture2d. It has 2 arguments. There's the main texture, and then there's i.textCoord. So this is simply just the texture coordinates of the current pixel. All the math has already been done for us. We just know that this is essentially where in the texture we want to sample, and this method samples that from the texture. Now, what we can do to apply a tint to this color is simply multiply call times our color, like this. And this works for tinting because if you imagine just the red value of color, if color was completely white, we wouldn't want anything to change. And the way this data is represented, if it's completely white, it's just 1, 1, 1. And multiplying things by 1 doesn't change anything. If this color was completely black, we'd want it to also tint it to be completely black. And so that would be 0, 0, 0, and that would multiply against the values of color to be 0, 0, 0 as well. And so if we return to Unity, we should see that now we have our first very simple modified shader where we can modify and change the color of this to anything we please. So there it is. That's the very first one. Hooray, we did it. Now let's move on. That's nice and simple. But I know you're wondering, well, can't we do something much cooler? And I'm here to say that yes, we absolutely can do something much cooler than this. So, as we saw earlier, we have access to the texture coordinates of the current pixel we're at. But this just takes it right out of the model data and applies it. What if we made another shader where we were able to modify or use other data for the UV textures? And so for that, the second shader example that we're going to write is a screen space UV shader, which will essentially, instead of seeing this checker texture neatly mapped onto the cube, whatever the shape is, we'll simply see that checker texture. This is sometimes fun to use for debug materials, but there's endless possibilities for the effects you can do with this. And I'm going to base this texture off of the old classic which is normal diffuse. I love to use normal diffuse because it looks pretty much like the standard shader for all intents and purposes, and it's very simple and easy to modify. Visual Studio will jump in front. We've got normal diffuse. I'm going to rename this to diffuse screen SPUV for screen space UV. Yep. Now we've got to open that up. So you can see this is an even simpler shader than the unlit shader. So why is that? There's got to be a reason, and it is because of one of the great shortcuts that Unity allows us, and that all is contained in this line: pragma surface surf Lambert. So in my presentation earlier, I talked about pixel and vertex shaders, but there's actually another type of shader pass that Unity gives us access to called a surface shader. This is very handy because what a surface shader is it's essentially the same as a pixel shader, but it already does all the work of lighting for us right out of the box. So you can see here, this is the same type of shader. Instead of call, it's called C, but it does essentially the same thing. It's the main texture. It gets the texture coordinates, or the UVs. It multiplies it by the tint color, and then it applies it to the albedo and the alpha. The albedo is essentially just the color without any lighting. Now, as we can see, there's no lighting happening here, but if we take cube and, I forgot to type in a new name here. I'll call this workshop / screen space UVs. And I open that one. It has lighting. And that's because, well, when this shader is compiled, Unity automatically adds all the lighting code around the code that we put in to this surface texture, thus lighting the cube without us having to do any work at all, right out of the box. So now we can begin making some modifications. So the first thing I'm going to do is I'm going to add a property. I'm going to call it UV scale. And I want this to be, so the second argument here is essentially the label that you'll see in the editor. So call that UV scale. And this is a vector type. So we have to type in vector. That way Unity knows where to put it. And we can initialize it with a base value of 1, 1, 1. Okay, so now we have UV scale up here. And as I mentioned earlier, we also need to define it in our script. And because it's a vector, I'm going to make it a float 3, which essentially means it's a vector with 3 values, and it's made of floats. And the name has to be the same. But now we have access to our UV scale. Now, we're here. We have the main texture, and we have our old texture coordinates. This is all well and good, but what if we want more information? Well, in this input thing, we get a value called UV main text, and Unity supplies this for us. There's actually other data we can get in input. And if I open my Chrome window here, you can see I just pulled up the page called built-in shader variables. And this lists all the various things we can get from Unity. So if we look, what was that first one called? UV main text. That's not described on this page, is it? I'm not going to search for in the documentation for exactly the page where it describes it. You can, however, if you type in float 3, actually it needs to be float 4, and call it screen pause. Unity knows about screen pause, and it will supply it for us automatically. So I can simply go in here, and if I type in screen pause here, and then we come back out to Unity, we'll see that we've got a error for some reason. We've got two errors actually. Text 2D, no matching two parameter intrinsic function, unidentified identifier, undeclared identifier. What's the problem here? Let's take a look. I know what the problem is. It's because I just typed in screen pause, but it comes from input. Simple mistake. It needs to be in.screenPause. And that should fix the problem. And now, as you can see, it kind of works, but it looks a little strange. And this is actually because we're in the perspective camera. If I click here and go into the orthographic camera, it's very small, but you'll see it works perfectly. We're seeing a mapping of that texture onto the screen. So we'll have to do a little bit more math in order to make this work for us with the perspective. So it reminds me of Chowder. That would be a really good application of this, is you could actually use a like watercolor kind of paper texture, and then just you use the paper texture, and then all your 3D models would have the paper texture on top of them, but they could all have their individual colors. You could make a very cool effect that way. So we need to do a little bit more math than this, unfortunately. So let's make a variable, a float2, to hold our screen position. And we'll call it texture coordinate equals that in dot screen pause dot xy. This is an amazing feature of shaders that I wish existed in other programming languages. It's called swizzling, which is a very fun name for just a programming language feature. And what this essentially lets us do is screen pause is a float 4. But texture coordinate is a float 2. We only want the first two values, so we can add .xy. If we removed this, it would automatically take the second or the first two values. But this opens even more flexibility. Imagine if we wanted to flip things, we could do .yx, and that would also be valid. Or if we were using a color, we could do this as like RG, and that takes the first and second one. That's another shortcut. We'll just do XY for now. But this opens up a lot of freedom, and I think in some of the later shaders I use it creatively. So the math is a little bit like, if you know how to do it, you know how to do it. I discovered this by looking up how to make this a couple years back because I wanted to make this effect. But the way to make things work in screen space, if I can type correctly, is that you actually can divide over in.screenPause.w, which is the fourth float in the float 4. This is a handy value that it provides to you that allows you to correct for the distortion that you get from a perspective camera. So if you come back in here, well, we've got an unidentified, or we've got an undeclared identifier texture coordinate. So it seems like I simply failed to type it incorrectly. If you come back here, it should, well, it doesn't quite work yet. We need to do a little bit more math here. So one thing I'm going to do while we're on our way is I'm going to correct for the aspect ratio. Right now the screen is a square, which is very convenient because our image is also a square. But if we didn't have a square screen, the image would be stretched. And here I can actually demonstrate that. What's up? Texture coordinate. Oh, I'm not using it. Wow. That would also do it. Yeah, let's drop texture coordinate in here. Handy. Hey. And now it actually works like this as well. But as I was saying, this is just tiling it out. We need to correct for the aspect ratio, which is pretty simple. We just scale the x by the aspect that we calculated. And let's also actually use that UV scale property we defined earlier. And that should allow us to take a look here at this cube material. We could scale it on the X, we could scale it on the Y, give it about 10 of each. And that's a pretty funky effect. Hello, Galdoc. Welcome to the workshop. And we can scale this to any old place. We can put any texture on here. This in itself is not that useful of an effect, but there's a lot of interesting ways to use this, and it's a good demo of how we can put any data we want into this UV's position. That's the beauty, to me at least, of shaders, is you can really get wild with what data you're using, and that's where most of the most fun effects are. So now we know how to bring our own properties into shaders. We know how to edit the UVs. Let's learn another very valuable tool, which is the clip value. And in order to do that, I'm going to demonstrate how to make a clip circle shader. And by the way, in this project, there's nicely commented versions of all the shaders that we'll be using today. So you can see here that the grass is clipped when I use the clip circle material. But let's make a fresh one from scratch. So I'm going to come back in here. I'm going to grab another copy of normal diffuse. Oops, I wanted to rename it. We'll call it diffuse clip. Open that up in Visual Studio. Go ahead and give it a name here. Workshop/clip. All right, now here we are in our new clipping shader. So we're going to need some more properties for this effect. We'll need the radius. We'll call that circle radius. And that's a float. We'll set that equal to 1 to get started. And we'll need a circle center. Circle center. And what this will be is a vector around which the circle is clipped. We'll call that a vector. And then we'll make that 0, 0, 0, 0. Okay, so the next thing we're going to need to do is we're going to need another thing in input. As we learned from the screen space UVs, we can get screen position. But another really handy one that I like to use is the world position. And this, in the pixel shader, is essentially the world position of the pixel that we're rendering, which is useful in a lot of different ways. You could do things like make a fog effect by measuring the distance from the camera to the pixel and then coloring it more white as that distance grows greater. In fact, that's how Unity's fog works, using different math to calculate exactly how white or whatever your fog color is, how much of that value is added. So the first thing we'll need to do from this effect is calculate the distance from the camera. Follow that distance from cam. And there's a very useful method in CG shader language called distance. And in it we'll put in dot world pause. And then we'll also add, well, we'll do underscore circle clip. Now we'll use the clip method. So let me talk a little bit about what the clip method does. So the clip method, if you pass in a value that's 0 or less it simply discards the pixel. So if I enter in -1, and we come back here, we'll take a look at our cube as an example. I'll use workshop clip, unidentified identifier, or rather undeclared identifier circle clip at line 27. Aha, see, I'm using circle clip, but I made the classic mistake of forgetting to define it up here. I always do that. Even after writing shaders for a long time, I forget I have to define them twice. We should be able to come here, circle clip at line 29. Oh, I wrote circle clip and it's called circle center. Silly me. There it is. We can see it's just not there. Those pixels are clipped. We can still see the shadows, and we'll get in on to how to get rid of those in a little bit. But if we were to pass in 1 instead, then of course all the pixels are shown. Now, the reason why we would do this by passing in a value that's less than or equal to 0, instead of doing an if statement, is, like I mentioned earlier, the pixel shaders run a lot of times per frame, millions of times generally. And the way graphics card architecture works, in order to do an if statement, which you can do, it actually has to do the math for, or rather, it has to do the processing for each case of the if statement, if it's true or if it's not. So one if statement can double the amount of work you have to do. So it's much better to try and work with just values. And the way we're going to do this is if the distance from camera, which we, or rather the distance from the circle center that we got, I'm getting ahead of myself, distance from cam minus radius. So that is to say, if the distance, let's say we're 10 units away from circle center, this will be -10 minus radius, which if the radius is 10, this will be 0, because we'll be right at the edge and it'll be clipped. If the radius is 15, it'll be -10 minus 15, and then we'd still get clipped. But if the radius was smaller, that math would work out. So let's take a look at how this works here. Well, we can see that this cube it's right at 0, 0. It's not clipped. Here, let's do this with the grass. This cube is not a good example. Workshop. Clip. Make the radius positive. All right, we've hit on a classic situation where the shader just doesn't work. So this is some live debugging time. Let's figure out what's going wrong here. Distance from camera equals distance. We have the world position. Let's first make this based on the camera position as well, because the camera will move, and we want the clipping circle to stay in the same place relative to the camera. Got radius. I think that might fix it. We do that. Okay, that did the job. Now, anything that's away from the camera is clipped. So let's see if we can move this here. Here. Genuinely enjoy live debugging. It's always fun to see what the problem is. Why wouldn't this be working? All right, I'm gonna go on my notes here and add a few more things from the version of it that I made earlier, and we'll see if we can figure out what's making this not work. The only difference still is that because I don't want the clipping to happen on the vertical space. I only want it to happen on horizontal. So instead of measuring the distance from these vectors wholesale, I'll just use the x and the z value. And if I do the x and the z value here as well, that way we'll be measuring just on the x and z plane, which means that those tall rocks that we had in the background, those will be only clipped on the x and z plane. And that should be center. Let's see if that helps. Circle radius to 10. We'll move the Z up, Z down. Curiouser and curiouser. I sort of expected this would happen. From camera. This is all good. More than that distance, the clip value. Yup. Circle center. Got radius. Got type opaque. Okay, so let's see if we can't figure out what the problem is here. Let's work backwards. So wouldn't you only get a positive value if the radius is negative? That could be true. I might have my math just wrong here. Let's find out. If I make this negative, oh, that was it. I just have radius backwards. I think if I add radius, that'll do the appropriate thing. Isn't this why people like game development streaming, is you have people to help solve your problems? So we'll make the radius of 30, and then let's add some x so that it's out here. The math's too quick. Yeah, so now we can drag this around, and if we want this to affect everything, not just the grass, we can simply select all these other materials and make these workshop clip as well. If we simply copy 30, here, I'll just select all of these. We'll say 30. All this to 0. All right, now we're in business. So now we have some. Now we can see our scene, and if we click play, clipping is working. Let's center the camera a little bit more nicely. This can be a little tricky because it's based on screen space. You got to do a little bit of lateral thinking to move the camera. Yeah. Then we'll move that clipping space to here. And then there's that. Now you might notice, I don't know if it comes through in the stream that well, but there's still some lighting around. There's a simple fix for that. One of those things to just know. If you look in the project, I've commented this on these scripts. If you add shadow here, that's a processor directive, that simply essentially says, we're going to do some stuff that's going to affect the shadows. Do the shadows afterwards. This shader really complements the Kenny style assets. Yeah, I was pleased once I got these basic assets in here, how nice it all started to come together. And now here, like this could be the aesthetic for a little game. You could do a little puzzle game. It doesn't let you look too far, so you can keep your world nice and simple. You can see here everything pops into view. So there's our first like really nice effect shader. You could also do like a fall off around the edges, absolutely. I've before written a really nice version of this effect where it uses a noise texture to give a nice like noisy like crunchy edge. All right, quick question. How does coding a shader differ from using shader graph? Are there things you can do in one environment and not the other? So essentially what the shader graph is doing behind the scenes is it's converting your instructions into shader code. Oh, no, it wasn't already addressed. That's fine. The reason that I still personally prefer to write shaders is because you get a little more access and it's a little easier to do kind of wild and crazy stuff. Shader graph makes you like follow the rules a little bit more. But almost everything you could do in a shader, you can do in shader graph as well. I just haven't invested the time to learn all the different minutiae about shader graph. And I've also found that for some of these effects, it's, especially this one, personally for me, it's actually harder to implement this type of thing in shader graph. But that could be because I'm familiar enough with shaders to not be too scared of all this stuff that's happening here. Because in the end, this is quite simple. We get the distance from the camera, and then we hide the pixel if it's not within the right radius. So that's our first effect. So let's do some other fun stuff. We got a few more left to go. This is one of my favorites, and this is a classic example of a vertex shader, which now we're going to be getting into. We've been doing all these pixel shaders. Now it's time for the real fun. I've saved the best for last, and that's vertex shaders, because you can really do some stuff with vertex shaders. The first thing I'm going to make is what I like to call an inflate shader, because it kind of looks like you blow up things like a balloon. I'm going to go ahead and flip all of these back to standard, so we just have our simple normal world. And I'll do a quick little demo of this. So we have this character, and what the inflate shader will let us do is actually physically inflate the character. Make him very large. We can also go the other way. We can deflate the character and make him very slim. And this is a very easy shader to write. So let's get into it. We'll put it back to standard for the time being. So I've got my new fresh normal diffuse. I'll call it diffuse inflate. Open that up in Visual Studio. Okay, so now you might look at the legacy shaders diffuse and think there's no vertex shader here. How can I do vertex modifications? It's simply not here because diffuse inflate doesn't do anything special to modify the default vertex shader behavior. However, we can add it, and all we have to do is define it. So this pragma value, it defines our surface function. It's called surf, and it uses the Lambert. We're going to make a vertex function. We're just going to call it vert. We'll come down here above surf. I tend to like to put the vertex shader above the pixel shader because it happens first in the pipeline, and that'll be void vert. And it's going to have some input and output. Another nice thing that shaders do is the in-out type, which simply says that this app data, which is another piece of data populated by Unity, will go in and out. And let's call that V. That's the standard in the Unity shaders from what I've seen. And almost all the things I've learned about shaders has been from copying them from different Unity shaders. So this one is very simple. So V gives us access to the vertex. V.vertex is the shader that we're currently running on. As I said earlier, the vertex shader is run for every vertex for every frame. So we also have the .normal, which is the normal of the vertex. For anyone who doesn't know, the normal is essentially a vector pointing basically out. So if we take a look at a cube, this is handy because these arrows kind of match the normals of the faces of this cube. This top face would have a normal pointing directly up, a normal pointing out. Basically, it points out, and we'll see that when we use it here in the code. So all I'm going to do is v.vertex.xyz. We don't want to modify the w in this case. And we're going to do a plus equals to add the normal. And if we do that, at first, it's not going to be good. As we can see, oh, forgot to add this up here. Workshop/inflate. This is too much inflation. He's simply too large. So we gotta pull this back a little bit. And this is a great opportunity for me to bring in a range. So we'll call it inflate amount. That's inflate amount to the inspector. And we could just call it a float and then call it a day. But there's also a nice semantic called range. And we can do -0.01 to 0.01 because he was way too big right now. Make that 0 to start. And like before. Have to define it in the body of the shader as well. And we'll just multiply the normal times inflate amount. And with that simple modification, we can use the slider to inflate or deflate. This is a good opportunity to talk about how vertex shaders affect the way Unity sees things. As you can see here, there's this orange outline. That's where Unity thinks the boundaries of the mesh are. It's worth noting that while vertex shaders can do some crazy stuff, Unity doesn't know that he's large. It won't change the colliders. It won't change many things. There are ways to get this data back, but it's just a word of warning that you won't. There can be some strange effects if you do too much with vertex shaders, because Unity doesn't know anything's changing. But now we can inflate this fellow, and yeah, we'll watch him run a little bit. Oh, I should have made a closer camera. Here he comes. Look at that. And we'll try it the other way. Love that. So that's the inflate shader. Very simple. Like I had to add this vertex shader, but this is at least to me, this doesn't seem like the most complicated programming. It's not the most complicated programming in most video games. And like I was saying earlier, Unity does almost all of the hard work for us. We can just copy their built-in shaders and modify them to create effects. So let's do some further stuff. Let's try and do some crazy stuff to the level. The N64 big head days. Oh yeah. There's lots of different fun things you could do. You can inflate them. You could also, there's different ways you could mask it so that it only inflates the head. And as I can see here, we've got that lighting issue again that I mentioned earlier, because it's calculating the lighting before our vertex shader. If we just put add shadow afterwards, that fixes everything up so that the lighting is appropriate regardless of what our settings are. That makes his shadow big and huge also, or super slim. So this level could be a lot more interesting. Right now it's just a flat world. So let's try and add some visual interest. Tiny paper man. He's not going to be able to get away from these zombies, that's for sure. He's a little more it's like Flat Stanley. All right, let's make another one. Let's bring in another normal diffuse. Normal diffuse is like it's my old friend. It's the best one to modify. And let's call this one diffuse wavy. So we're gonna make some waves. Diffuse wavy. I'm quickly gonna do add shadow because we'll know we'll need that. And I'm gonna go ahead and define that vertex shader like I did in the last one. Vertex, vert. Okay. Void. Just setting up the same things that I did in the last shader. And let's get our vertex position in world space. So it's worth noting, it didn't matter for this one, but this vertex is in object space, which means that, for example, no matter how I got to grab a little higher up. No matter how I rotate this fellow, the effect remains the same. And similarly, if I did inflate, but instead of the normal, I just added, let's say, point y plus equals 1, which would just lift him up on the y, or rather goes the other direction. No matter if we rotate it, it's not lifting him up in this direction. It's rotated with the object. So we're going to need to get that in world space. Return this back to the way it was. So we'll call that vertex world position. Now, we're going to use another great built-in variable, which is unity underscore object to world. Now, this is a transformation matrix, which are scary, and I still don't fully understand how they actually work. And I took 2 different classes in college that were supposed to teach me how they actually work. But I do know that if I simply use mul, which is the multiply method, and multiply a vector by it, it converts it into world space. So now, this is the position of the vertex in world space by multiplying it. And at the end, we'll say v.vertex equals mul unity world to object vertex world position. So that basically reverses the effects of this, and it goes from world space to object space before we assign back to the vertex. Now, anything we do here will be in world space. So I could say, for example, vertex world position dot y equals vertex world position dot y times 2, and that'll stretch things. This guy still has inflate. So let's give him. You see, I did it again. I just left it up here. Workshop / wavy. We'll give him workshop wavy. Oh, we've got an error. Invalid subscript y at line 26. Let's take a look. 26.y equals vertex world pos dot y times 2. What would the problem be here? Vertex world position dot y times. What if we simply do it without the y? This will multiply it in every angle. Cannot implicitly convert 4 by 4 to 4 by 4. At line 28, vertex world position equals vertex world position dot 2. It's declared as float. Haha! Thank you. You're absolutely correct. It's defined as float and not float 3. That is precisely the problem. It was a test, so someone in chat can participate. Now we can see that he's tall, big and tall. But maybe we want everything in the scene to do this. So what I'm going to do is I'm actually going to assign every material here to be workshop wavy. And now it's all tall. It's all been stretched up. But we want to make it wavy. We don't want to make it stretched. Why does this look different? This shouldn't look like this. Something's going on. V.vertex. Ah, it's because I called it. So this is a great example of why I try to always make things float 4s, which is that because of that perspective camera thing I talked about in the screen space UV, where you need a .w, the same thing applies with positions. If you lose that .w, you lose the projection of everything, which you don't actually have to worry about modifying that w value, but you just have to make sure you don't lose that precision. Alternatively, we could make this a float 3 and then do v.vertex.xyz and make that the xyz of this. So we leave the w the same. Well, I guess that doesn't work. I thought that would work. I'm going off script. Anyway, let's stick with what works. So let's do some transformation. For waves, I'm going to use a sine wave. It's a classic wave. You could use any trigonometric function here, but I'm a fan of sine waves. So we'll just define some values. We get a sine frequency. That'll be a float. We'll start that at 0, and we'll get a sine amplitude. So we'll set that to 0. So that's a float sine frequency, float sine amplitude. And the wonderful creators of the CG shader language were nice enough to include the trigonometric functions for us that are available for us to use. So we'll do plus the sine of the position on the z, which is, there's going to be an error, but it's this direction because we want it to be wavy as they're walking. Well, this could be any axis really, and we'll multiply that by sine frequency, and then we'll multiply all of that by the sine amplitude. And with that, we can control these values. We'll set it to 0.1 and 5. It's made things wavy. Now everything in the world is being scaled by these values. So we can add some steep hills. We can flip the direction. You can really do some wild stuff here. Now we're really starting to see the limits of the system. And this is where things get the most fun to me, is when you can make crazy stuff like this happen. There's just so much potential. Now, one thing that's important to note, and this is a key example of this, the vertex shader can only work with the geometry you have. So the example here is this ground looks completely jagged. If we look at it, it looks like some paper folded into an accordion. And that's because that's all the geometry we have. It's not a very high resolution ground. The solution to that would be to simply have a more high resolution mesh. But for the case of this, we're just gonna turn the effect back just a little bit, 0.1 and 5. It just seems like a good teachable moment. And so now everything's wavy. And I think this heralds back to, this reminds me of a particular video game. And I think a good way to close this up is to create a Animal Crossing style shader that puts them on sort of a barrel world. This will be the most complicated one that we'll write, but I think you'll find that it's reasonably easy to follow along. So I'll drag in a new diffuse shader. Actually, no, you know what? In the spirit of modifying shaders, I'm going to demodify the wavy shader. So I'll duplicate that. Diffuse wavy 1. We'll rename this to diffuse AC. And we'll call it Workshop Animal Crossing. We won't need these properties. Get that out of here. But we will want this vertex world position multiplication business because we're going to want to do this effect in world space. Let's go ahead and set up all our materials real quick. We call it Workshop Animal Crossing. Everything should be back to being good and flat. Now, at the risk of seeming hand wavy, I am going to bring in a code snippet that I have written ahead of time, which is simply some quaternion math. You could see, just looking at this, why I might not have wanted to write this during the workshop. I've linked here the blog post that I took it from. That was for GLSL shaders, but all I really had to do was change vec4 to float4, vec3 to float3, that type of thing. And this code just works. And this lets us use this method, rotate vertex position, which is hugely valuable for what we're about to do. So let's add some properties. Oops. We're going to want effect amount. Make that float. That way we can change how curved the world is. And because we don't want the effect to happen right on the camera, similar to the flip circle one, we'll create an effect offset And we'll make that a vector. 0, 0, 0, 0. And we'll define these down here. A float called amount, and a float 4 called effect offset. So now in the vertex shader, we can do our good work. So first, let's calculate the offset. We'll call that just offset. So we'll start with world space camera position. And I don't think I mentioned it last time. This isn't defined anywhere in the shader. This is another one of those great handy variables that Unity gives us. And this one is actually built in to this, I think. Yeah, world space camera position. But you can also do a lot of crazy stuff with time. Like you get the time in a shader. There's information about lighting. But I digress. You could do something with where the UVs are animated over time using sine waves and have some crazy textures that way. But we'll do that plus the effect offset. In that way, the effect is always centered around a point that's the same relative to the camera. We'll want an effect distance. And I could use distance, but I'm not going to because I want the distance to be able to be negative. So I will just minus offset from the vector world position. So that way, if vertex world position is less than the offset, we'll get a negative value instead of kind of the absolute value of that. So then we'll do vertex world position .xyz, because we don't want to modify the W. And we're going to use that rotate vertex position. And this takes in a few values. We'll pass in our vertex, which is simply that value. So this takes in the vertex, the vector rather, to rotate, the axis to rotate it around, and the angle to rotate it. So to define the axis, we'll just put in a new float 3 here, and I've put 1 in the x so that it'll be on the x-axis. And then we'll do effect distance times underscore amount. And we can see how this works. Hint, it's not going to work perfectly. Oh, hey, it looks pretty good. Our effect offset works. But if we click play, it looks good for a second, but we can see that things start to get strange after a while with this. And I actually ran into this while I was writing this shader. So I thought I would leave it in because it's a good reminder that even though we're measuring it based on how far the point is from the camera position, we're rotating the vector around a point that doesn't change. And the solution to that is simply to, before we do the math, move us with the camera, and then so that we're not actually changing things, we'll add that back afterwards. So we're essentially changing into camera plus the offset space before we do this math. And now if we come back in, everything should look about the same. Once we enter play mode, they should run on this little Animal Crossing world essentially forever. We can change the effect offset. We can have them going uphill. We can have them going downhill. If we want to, we can negate this and have sort of a tube world. We can turn it up really high and make things all crazy like this. Same in the other direction. And if we wanted to, we could do this. So we have the x-axis here. But what if we did this on a different axis? If we did this effect on the y-axis, well, it's as if they're kind of running around a circle. We can put this in the other direction as well to make it seem like they're always turning towards the camera, running around the inside of a loop. And we could also do one of my personal favorites, which is around the z-axis, which almost makes it look like they're running along a strand of DNA or something along those lines. But this is a great example of how, using the data available to us, we can change the data we give to Unity to distort the world in crazy ways. And we can see here this kind of twist of a world that they're running on in the scene view. And with that, I think that just about brings us to the end of the content that I have prepared for us. If anyone has any questions about maybe how I would approach any other types of effects, I'd love to field those. But in the meantime, I believe that should be the building blocks of how to get started with shaders. Looking here at my slide deck, I've got some useful links here. Let me run through these real quick because there's some useful tips. I've tried to make this as good of an asset for someone coming in. I'd love to give credit to the beautiful Unity surface shader examples. This is a great tutorial that covers some of the stuff that I've covered alongside other things. Here's that normal inflate shader that I showed you earlier. There's a link to the GitHub where you can download these shaders that I've written, or the template project, and mess around with it yourself. I've linked Alan Zucconi's website. He's basically the preeminent shader tutorialist on the internet. I've learned so much about shaders from him. There's a link on where you can download the shaders you need for Unity. There's a link to kenny.nl, this amazing website with tons of great free game assets. And finally, the documentation page for Unity's Shader Lab reference. GalDoc. So if I wanted to make a 3D graphing calculator with this sort of thing, and I want to be able to not calculate values that would either divide by 0 or give complex results, how could I accomplish this without if-then logic? So the easy answer is to check the values that you're passing into it before you give them to the shader. There's something that I didn't cover, but is described in the Unity documentation. There's a quite easy way to modify these every frame. And you could check your numbers ahead of time. But I don't think I know quite enough about 3D graphing to necessarily know if that answers your question. Does that cover about what it is? Probably the best way would be to validate your input before you give it to the shader. Or perhaps the shader might just handle it gracefully. I found shaders, for all the difficulty in getting them to actually work, often handle that type of thing reasonably well. Any other questions? Yeah, GalDoc said they have two. I'll give them a second to type that. In the meantime, I'll get crazy here. And let's combine some effects. You're modifying a vertex based on a normal. In a cube, wouldn't a corner vertex have 3 different normals? So that's a really good point. Technically, so there's different normals for everything. A face can have a normal, an edge can have a normal, and a vertex has a normal. The vertex actually has one normal for the cube, and it points kind of off in this direction. It points directly out from the edges surrounding it. A useful way to think about it is, if this vertex has these 3 vertices connected to it, if you sum all the vectors pointing towards it, the sum of all of those will be the normal. So in the case of the cube, it points off in kind of orthogonal to the cube surface. And for edges, the edge normal is the kind of sum of the normals of the 2 faces on either side. So this edge here would kind of point off in this direction. And then the faces are simply the normal of the face. It points directly away from the face. That's a great question. I've also included in the project, is there a way to get those different normals inside the shader? There is a way to get the edge normal and the face normal inside of a shader. If I would have to look that up. How are shaders that make models and sketch generally done? So that's actually really interesting. For my class, Mathematics of Graphical Simulation at RIT, my team had a chance to write a shader that actually worked like that. And the way that that works is with something called edge detection, would be the keyword to look up, which is essentially finding the edges of the model from the camera's perspective, and then drawing lines around there. There's also a really cool thing you can do accessing the fragment shader directly, where you can say, okay, so I have the lighting value for this cube. Instead of coloring it just a flat, dark color, use a similar technique to those world space UVs to color it a dark color. Yeah, that's the way that I would approach that. So there's sort of twofold ways to approach that. The other thing that I found that's great is, because I think of the intimidation factor of shaders, there's a huge amount of resources online for basically any popular effect. So if you even were like, I want to make a cell shaded thing like Borderlands or the like Telltale games, you could type in Borderlands shader tutorial or shader example. Models with hard edges like the default cube usually have multiple vertices in the same position, one per face with a separate normal. Yep, that's another. It really depends on a lot of things. I'm actually not precisely sure how Unity handles it under the hood, because it really depends on how the folder is stored. In a FBX file, it is represented by different vertices. However, by the time that FBX file actually gets to us in the shader, there's a chance that Unity could have done pre-processing so that we have it represents it just as one vertex. Also, hello, Ashley Aurora. We're just finishing up here. Do we have any further questions? So yeah, this is CG shaders. So it's, look up here. Technically, it's the Unity's version of CG shaders, wrapped in Shader Lab. But when looking up code references, I usually type in CG shader and then whatever my question is. Where were the original shader default shaders files located that you copied into your project, or do you just use the create? Yep, I'll cover that one more time, because that's honestly one of the key secrets, is that if you go to the Unity download archive and go to whatever version of Unity you're using, in this dropdown, you can download the built-in shaders, and then that gives you this file, which has everything in here, including VR, including the mobile shaders, including all sorts of different shaders. And I have a link to this page in the useful links page of the slide deck. All right, so unless there's anything else, I think that might be just about it. Where's the slide deck at? Oh yeah, that's a good point. I covered it at the beginning. I have a link here. It's https://bit.ly/shader workshop. But if you want an easier to remember place to get that at, it's at my website, aidanmarkham.com. And I'll also be putting it out probably on my Twitter page, which is at Aidan Markham. Yes, that'll allow you to get a link to that GitHub. And as soon as the video for this workshop is up, I'll be linking the video on demand of the workshop in the links of the slide deck, so you could follow along later and see how I did anything. Right, so with that, I think that might be just about it. I don't actually know the procedure for dismounting here.
Yeah, I think we're good to go.
Yeah.
If you have any follow-up questions, feel free to drop them in our Discord.
Yep, absolutely.
You can find all the information to get in touch with ROC Game Dev and join our Discord at our website, rocgamedev.com.
That's about it.
Awesome. Thanks, David Kilmer. I'm glad you liked it.